about, let's say, n squared divided by 32, you multiply it by 25, because you have this for all pairs of x and y, and you almost discard all the effect from mid sets, it still works in n squared. Okay, so are there any questions regarding the previous problems? Any more questions? Yes?
The Q polynomial, the index of the B.
Yes.
When I is larger than n, it's negative.
I consider these indices like taking modulo n. So minus first index is actually n minus first. This is exactly like repeating the coefficients of p twice. Any other questions? So let's proceed to the problem A. The problem A was about the following. Well, first you need to analyze the input data in order to find the correspondence between how many products of different factories or how many. Okay, first of all, you find out how many products of different kind it is required to create one unit of a product of each type. So you calculate numbers like aij, such that for xi, let's say for each j of product of type j, you will require ci j equal to aij multiplied by xj, product of type e of type I for all I not equal to j. This can be found by the input data. After that, you need to solve the following equation. You need to solve something like that: xj minus cji minus sum of cji by I not equal to j equals to yj. This is we are given the number of products that should be left, and we have to choose such xj that the following holds. This is similar to xj minus sum of aij. This is a fixed number x xi equals to yj. This is for all j from 1 to n. This is a system of linear equations. It can be solved using the Gaussian elimination because of two high constraints. So one should use, the common trick is to use some iterative method that converges fast. I will not prove formally why the method that I will describe works fast here, but you may in fact represent it as a simple iteration method, and in computational methods course, if you have such in your university, I think you will prove that it converges pretty fast. So the idea here is the following. You start with some estimation of the answer. Well, the good estimation would be to start with the vector 0 vector. This is not the power, this is 0 vector. xj. Let's not use this indices. Let's say that you let xj be equal to yj. This is an estimation, but it is not really good estimation, because if you consider such number or such amount of products being produced, you will need some extra product from each factory that is required to produce at least that amount of product. So you start by letting this. You calculate the extra product for each factory. For factory J, it will be sum of I J multiplied by, so it was for J required A I J multiplied by I. So for you calculate such sum. For J, this is an extra product of kind J, and then you correct your estimation by letting xj equal to yj plus all the extra product you have forgotten to add. Okay, you do the following, then you repeat the process until notice that the number of product created by each of them, amount of product of each type during this process, it only increases. So at some moment, one may show it will converge to the actual answer of this system, and starting from some moment, then let's denote this xj with prime, the difference between xj prime and xj, the normal, the difference, will be pretty small. Put some epsilon here, and you may output that as an answer. Or the other way is to exactly write down the formula that is in the statement. In the statement, as far as I remember, they have computed the real y's built by your xj. And if the sum of squared difference is large enough, logarithm of 1 divided by the precision steps. So this solution works pretty okay, and many teams have submitted somehow similar to this, but faced some issues with time limit. I can't tell what exactly was wrong. I didn't see much into the solutions. Are there any questions regarding what I have just told? I know that this works well. This is what was submitted when we solved this problem. Okay, let's talk about problem E. Problem E was a final problem. It has a really complicated statement, although it is pretty easy. Problem E was about a tricky sequence. Let me write this sequence. One second. For example, for k equal to 3, the sequence was like 0, 7, 4, 3, 2, 5, 6, 1. 5, 6, 1. This is for k equal to 3. And you had to compute a large number of you had to answer a large number of queries. Each of queries looked like f of LR is a L plus a L plus 1 XOR a L plus 2 plus a L plus 3 and so on. So and one more extra statement. In this sum, the priority is chosen such that for even else, the plus sign has more priority, and for odd else, the XOR sign has more priority. This sounds really complicated, but let's try to understand what exactly that means. First of all, look at this sequence. There is a great property that this sequence has. Actually, each two adjacent numbers, I mean, if you divide numbers by pairs, group them into pairs like this, then in each pair, two numbers will be will give 2 raised to k minus 1 as a sum. For example, here 0 plus 7 equals 4 plus 3 equals 2 plus 5 equals 6 plus 1 and equals to 7. And if the numbers are such that x plus y equals to 2 raised to k minus 1, then it is also true that x XOR y is also 2 raised to k minus 1. Because their binary representations are complementary. When one number has 0, the other has the 1, and vice versa. So, using the fact that the priority here depends on the parity of L, you may find that, for example, if L is here and R is here, then in this sum you first consider the XOR of these two numbers and these two numbers and add it with a L plus the result of XOR plus the result of XOR. Or otherwise, if L were here, the most important operation will be plus, and you first plus add these two numbers, then add these two numbers, then add these two numbers, and XOR everything together. So, even though the sequence of 2 multiplied by 2k minus 1 plus the rest. So the only tricky part is how to calculate these remaining 1, 0, 1, or 2 numbers. In order to do that, it must be possible to find out which number stays on the position I in the resulting sequence. So you need to answer queries like find number on the ith position for k equal to k. If the sequence is of the length 2 to k. And since the recursive nature, we have the recursive nature of this sequence, you may, as usually, easily transform this query to the query with some another I, but to the smaller k minus 1 in a constant time. And indeed, look at these numbers. In first pair, I have chosen the first number, the second pair, the second number, the third pair, the first number, and so on. I claim that for any k, if you choose these numbers and leave only them, you will get the sequence for the k minus 1. And indeed, here you see the answer for k minus 1. 0, 3, 2, 1 is the resulting sequence for k equal to 2. That means that if your I belongs to one of these chosen elements, then you may easily call the find number of I divided by 2 and k minus 1. Otherwise, you know that the all remaining numbers are complementary to one of the chosen numbers. So you return not find number, but 2 raised to k minus 1 minus find number. So that works in O of k for a single query. That means that you can answer in O of k per query. That's really fast. Are there any questions for this problem? Okay. Questions? Okay. So the remaining problems are D, G, and I. They were not solved by anybody, but I was a bit surprised that problem G was not solved by anybody, because Problem D and problem I will require some thinking. And problem G is pretty technical. I think you should be able to solve that problem. So, what was the problem about? Consider the sequence of numbers. We will repeat the following process. Consider the largest number among them. If it is not less than the sum of the rest of the numbers, then we will call this number to be a winner and remove this number from the set. Otherwise, we just remove it from the set. Consider some number, some sequence of numbers, repeat this process, and find out the number of winners. And after that, we have several queries. Queries of form replace the ith number with x. And after each replace, we should report the number of winners in that sequence. So how can we do that? First of all, let's try to find out the number of winners in the sequence faster than in the linear time. Let's move not from the largest numbers to smaller numbers, but in the other direction, from the smaller to larger. This is still okay. Suppose that we have the sorted sequence. Suppose that F1, F2, F3, 4, and so on are already sorted. Yes, this was the problem. So, consider this sequence. What can we say about it? First of all, F1 and F2 are always winners. F1 because there will be no remaining numbers, and F2 because the only remaining numbers will be F1, and F1 is no larger than F2. Okay, what does that mean? That means that the next winner after F1 and F2 will be at least S equal to F1 plus F2. This is the lower bound for the value of the next winner. Because the next winner should be larger than the sum of the previous numbers, and previous numbers contain at least F1 and F2. Okay, let's find this first number that is larger or equal to S. For example, let this first number be F5. There may be two possibilities. Either F5 is a winner, so suppose that we have found number Fi. So the first possibility is that Fi is larger than F1 plus F2 plus so on, plus Fi minus 1, then it is a winner. And in this case, we count it as a winner, and we update the value of S with what? With the sum F1 plus F2 plus so on plus Fi. Because the next winner should be at least that large in order to be larger than the sum of the previous numbers. Notice that this is the new S. It is at least twice larger than the old S because it contains the first I minus 1 terms that contain S, and Fi is larger than S. Not smaller than S, so it is at least twice larger. Okay, this is the first case, and this is and there is a second case. Otherwise, Fi is not a winner because the sum of the previous numbers is larger than Fi, and we cannot consider it as a winner, but we still can update S. We know that the winner is somewhere to the right, and if it is somewhere to the right, it should be at least equal to the sum of all numbers that we are currently staying on. So we can still repeat the same thing. S prime equal, let S prime be equal to F1 plus so on plus Fi. And it is still equal, larger or greater than the old S multiplied by 2. So repeat the following steps. How many steps are we going to take? Since S is at least doubled each time, then there will be no more than logarithm of the maximum number of steps. Okay, This means that we are able to answer the single query in logarithm of maximum number steps. Each of steps requires us to calculate the sum on some prefix and to find the first number that is larger or equal to f, to some given number. So we need a data structure that allows us to perform queries of two types: the lower bound type query and the prefix sum type query. Is that clear? Yes? Okay. So let's think about such a data structure. Also, it should be able to allow us to change the value of a given number, because we also have some change queries. What can be such data structure? The most easy answer, it may be a, I don't know, a two-dimensional Cartesian tree, but it is really hard to implement. I will tell you this the pretty easy version that requires only Fenwick tree or binary index tree, whatever you call it. Let's do the following. First of all, we know all the numbers that we'll ever get to our data structure. We know all the original numbers, and we know all the numbers that appear in the queries. Let's sort all these numbers and compress them so that we can, for each number, find its index in a sorted list of all numbers. So now we can use the numbers as the keys in some data structure. For example, let's build a Fenwick tree. This is a Fenwick tree. Indices of Fenwick tree will be from 0 to n plus m minus 1. At most n plus m minus 1. If some of the numbers repeat, the length will be smaller. Now, what are we going to do? First of all, keep the set of all numbers that we currently have in our structure. This will allow us to perform queries of this type, the lower bound queries. So we keep two data structures, Fenwick tree and a set of what? Let's say of numbers of, let's say, set of all fi, of current values of fi. Okay, multi-set if you want. That will allow us to perform queries of this type. After that, how to find out the number of winners. You do the following. You let S be equal to the sum of two smallest numbers, and you find the lower bound, and then you have to find the sum of first I minus 1 or I numbers. How to find the sum of smaller I numbers? Let's use the Fenwick tree. Write down the following sequence. We'll store zeros on places of elements that are not currently present in set of F, and their values for elements that are currently present. So the sequence will be something like that. It means that, for example, if our current values of F are 6, 10, and 20, so our gatherings have now sequences of course powers 6, 10, 20, and so on. But at some moment of time, there will be also 2, 3, 7, 12, I don't know, 14, and some other values. For example, they have been at the beginning, or they are going to be after this query when we perform some change. No matter. At some moment, there will be enabled only those positions that correspond to the values of our current gatherings. After that, what we need to do, if we want to find the sum on the prefix in the fi, you find the corresponding index in Fenwick tree in a sorted array of all values using the binary search, and you get the prefix sum using the query on the Fenwick tree. It allows to compute the queries in logarithmic time. So the overall complexity of one query will be logarithm of maximum number multiplied by logarithm of n plus n per query. So this solution works pretty fast. Are there any questions? Yes, let's start with you.
The first log is from the number of the maximum number of features, right?
Yes,
top number.
exactly.
The second is the
From using the Fenwick tree to find the prefix sum.
and the binary search.
And the binary search, yes.
So the first log is the amount of maximum number of features, and the second log is for type of query.
Yes, it's for finding the index in sorted list with binary search and querying the Fenwick tree.
Okay, so the Fenwick tree is always sorted, the array represented by the Fenwick tree is always sorted regarding the sorting of the young.
Not simply the sorted list, but the sorted list with some numbers deactivated. You see, when some youngling disappears, for example, youngling F2 is replaced by youngling with great force, we cannot simply shift all the numbers in Fenwick tree because it does not allow such queries. So we replace him with 0, and the new value of his force replaced with the new value of his force. This is a way not to perform any shifts on our sequence. You see, the problems that have already, if you have all the keys known in the input data, you may come up with an offline solution. This is the solution that is offline. It uses information about all the queries that we have. How does it use it? Well, we have the initial force values, F1 to Fn, and some extra F prime, I don't know, F prime 1, F prime 2, and so on, F prime m, that will appear in our sequence. We get all of them together into a single list. We sort them, getting all, for example, let's call them V1, V2, and so on, Vn plus m. This is the list of all force values sorted. After that, when we have some force value, for example, we have S, we first find out to which position in this list S corresponds, and we use this position as an index in a Fenwick tree. We know that Fenwick tree stores either zeros or force values for all younglings in order from smaller to larger. Zeros are stored for those younglings who are not present currently, for those force values who are not present. And the actual force values are stored for those who are present. Do you understand the idea?
I have to later.
Okay, I think we may continue later. Any other questions?
Have a doubt.
Yes.
Yeah, on the right part, why S prime becomes larger than 2S?
For the same argument. You see, here we have some, we have the at least S, because S is the sum of some prefix that contained here. And Fi is also at least S because we have chosen such Fi.
Okay.
This is always held, and these may be held or may not, but this does not affect the correctness of this result. Yes. And are there any questions? Is everything clear? Okay. Yes.
The Fenwick starts and the number of guys with some value of force, or the actual value of the force.
Actual value of the force. It allows, okay, it stores either the actual value of the force or 0. There are two cases. If it stores actual value of the force, then there exists a guy with exactly that force in current set. If there is 0, then there is no guy with that value of force in current set. That after that, you see, when you get the sum on the prefix of this sequence, it is actually sum of several first youngest according to their sort, to their force level. the sorted order of their first level. We can't simply say how many exactly younglings we will consider when we get the prefix sum. But we overcome that by an additional binary search here. In this list we find the first youngling that has the force of at least S in this list using the binary search. And this list is easily mapped on this Fenwick tree. It has the same length as the Fenwick tree. We just take the sum of the prefix that corresponds to the position of S in this list in Fenwick tree. If something is unclear, let's stop after that. Okay. Let's move forward to the next problem. The next problem I think we want to discuss is the problem D. Problem D. Problem D was about some tricky multidimensional search of correct values of, I don't remember what, selectors, right? So we had some spaceship who exists in an n-dimensional universe. He has also n, what's it called? N engines, right? I forgot the name. He also has, let's say, it has n vectors and n selectors. Each selector chooses the coefficient that the corresponding vector is multiplied, and after that they are all summed together, and the resulting vector is the overall speed of the ship. So you are asked to find the correct, I don't remember, what was the word, selector for each engine, right? Okay, you need to find the correct position for each selector, such that the overall sum of overall speed, resulting speed, is 0. How do we do that? Well, let's perform that sequentially. Was there anybody who thinks that they have solved this problem but didn't implement it in time? Was there any team that just was out of time? No? Okay, let's discuss in detail. First of all, let's do the following. Let's try to find all the vectors xi that correspond to all our engines. How can we find them? Well, consider some state of selectors. For example, consider all Gj equal to 1. This corresponds to some speed, let's denote it V0. After that, perform 100 queries. 100, I mean n queries, such that in each query, all Gj are equal to 1 and Gi for some I is equal to 2. That corresponds to some speed Vi. Let's see exactly what V0 and Vi consist of. V0 is the sum over all I of Ki1 multiplied by xi. Xi is a vector, and let's say j, and vi is the sum over all j from 1 to n kj, and here 1 or 2, depending on if j is equal to I of each j. So in this sum, in these two sums, all terms are the same except the one term for the ith direction. The difference between vi and v0 is some coefficient equal to ki 2 minus ki minus ki1 multiplied by xi. Denote this vector as bi. What are these vectors? These vectors are proportional to the vectors of xi. We do not know the xi, but we know some vectors proportional to them. And also, according to the statement, we know that each vector in the n-dimensional space may be represented as a linear combination of xi. That means that if we multiply each vector from xi by some non-zero number, we will still have a basis of that space. The xi form the basis and bi also form the basis. And we know bi. That helps us in the following computations. When we have the basis of some set of vectors, we can easily perform any linear operations, expressing any vector as a linear sum, linear combination of basis vectors. So, what are we going to do next? We have like at least 19 queries remaining. 19 queries is not enough for doing anything, for working with each direction separately. So we need to do something in parallel. There's a technique that is called parallel binary search. Does anybody know about parallel binary search? Please raise your hand if anybody heard about that.
Just hear about it.
Just hear about that. Okay. I should have added the question there. Okay. Let's discuss more about parallel binary search. The idea is pretty easy. We will perform. Okay. Let's fix one engine. For example, let's fix the first engine. How can we understand when we make a query? How can we understand that the selector position for this engine is too large or too low? You know, starting from some position, it is too large. That means that this engine will add positive amount in the direction of xi. And starting from and to the left, it will be a negative amount in the same direction. What does it mean? Some amount in the direction. You know, when you perform a query, you have as a result the overall speed v. The v may be expressed as the sum of alpha I multiplied by bi, because bi is a basis in our space. We may find all alpha I using, for example, Gauss elimination. Okay, suppose we have such alpha I. Then we may see that what are actually alpha I? Alpha I is actually a following number. It is actually a ki gi divided by well, if we had expressed okay, let's rewrite it differently. From the other point of view, this is the sum of some beta I multiplied by xi, because vector bi is proportional to the vector xi. But on the other hand, we know that V is the sum of Ki Gi multiplied by Xi. So we know that beta I equals to Ki Gi, and also we know that alpha I is equal to what? It is equal to Ki Gi divided by Ki2 minus Ki1. Because Bi is that times larger than Xi. So what does that mean? It means that if we have numbers alpha I, and we have them because we may perform Gauss elimination and express V as a linear combination of B, and we know V, we know all the V's, so we know alpha I, so we know this number, and if this number is, we can compare this number compared to 0. If this number is positive, it means that Gi, the selector for the ith engine, is too large, which we should reduce it. If it is negative, then we should increase it. And if it is 0, then okay, we know the exact position for the ith engine. That results in a zero speed along Xi. Is this idea for a single engine clear? Did everybody understand what I mean here? So, if we could, we may have just performed a binary search for each engine. For each engine, we would just start it by setting some left position for selection, some right position, trying the middle position, and if it is too right, then we shift right to the middle, otherwise we shift left to the middle. It's a usual binary search. But we can't do that because we have only 19 operations for all 100 engines. So we need to do something in parallel. How do we do something in parallel? Very easy. Actually, we in one query, we receive information not about only one coefficient. We receive all coefficients that we have. So let's do the following thing. Let's keep, before the ith step, we know that Li. No, before some step, we know that Li and Ri, such that Li is smaller than the optimal Gi for the ith engine, and it is smaller or equal than Ri. So before the, for example, some step, the beginning of step, we have 100 L's and 100 R's. Those L and R correspond to the binary search bounds for each of the engines. This may be drawn like this. For each of the engines, we know the bounds such that the optimal answer is around them. This is the first engine, second, third, fourth. This is L1, R1, L2, R2, and so on. What are we going to do? For each I, choose the Mi equal to Li plus Ri divided by 2. This will be the point for I, the value of selector of the ith engine that we will try. Ask, perform a query with such Gi. It will result in some speed V. Okay, express V as a sum of alpha I Bi, alpha I Bi. Look on all alpha I, and for each I, if alpha I is larger than 0, then Ri should be assigned to Mi. Otherwise, Li should be assigned to Mi, and if it is equal to 0, then you have already found the correct answer for that I. So this means that using one query, we perform one step of binary search for all n engines. That means that we should use only 1 plus n plus log n queries. Log not n, but log how many positions each selection has. I don't remember which selection it was. Maybe also n. Well, that means that we have solved our problem in like 110 queries or 11, something like that. Are there any questions for this solution, for the parallel binary search technique? This is a very important and pretty regular idea. Regular, I mean it appears on contests pretty often. So I advise you to try to understand what happened here. So are there any questions? Looks like everything is clear to everybody. It's really a big surprise. Okay, so if there are no more questions, last chance, then we are going to the problem I. Well, you want the question?
Yeah.
Fine.
Where can you find other problems about this? Like
For this technique, for parallel binary search,
Yeah.
I will send you. Okay, I will send you the list of several problems that come to my mind. Some problems from cold sources, from other online judges. I think I'm going to send you both the problems for geometry and for some themes that appear here, just as a separate list of problems for you to solve in free time if you want. So, okay.
Can this problem if you're something about meteors, binary search, I think it's from Chef.
Meteors.
I saw some description in book forums about the problem.
Okay.
It was like
If you find out the link, you can send it to me. I can also share it with them. So let me somehow mention that I should. Okay, and the last problem, the problem I. The problem I was, well, unfortunately, you do not have the solution of problem I in this paper because it's at the time I have written this paper, I didn't know how to solve it. And, but right now, I have come up with an idea using the help of the author of the contest. So let's discuss it pretty briefly. I'm not going to prove almost anything, and I leave it as an exercise for you, as usual. Still, if some of you are interested in how we can prove that, we can discuss it. I think I understand the key idea. So, the problem I has the really simple statement. It was about the minimum spanning tree, and we were required to change the minimum number of edges in a graph so that it has a unique minimum spanning tree. Also, that graph had contained the small number of vertices, like 20 vertices and like 100 edges, something like that. So what's the idea? How can we solve this problem? Let's do the following. Let's start from the, first of all, let's remember how we can find the minimum spanning tree. Let's remember the Kruskal algorithm. Kruskal algorithm works like the follows. Yes?
sorry, for the solution.
Okay.
The problem asks for the minimum spanning tree must be unique, but it doesn't have to be the same weight from the original, or
No, it may be.
It can be larger.
It may be larger. It may be. The only thing, it should be unique. As far as I remember. Correct me if I'm wrong. I think it should. It does not require for it to be a unique, to be minimum possible weight. Minimum possible weight is simply 1 plus. And no, okay, maybe. Still, the statement does not require for the minimum spanning tree to have the minimum possible weight. Is that correct? Did anybody read the problem? Okay. Well, so back to the problem. How does the classical algorithm work? It considers the edges starting from the minimum one to the larger ones, and it performs several unions in a DSU, just disjoint set union. Which unions does it perform? Well, we already have several connected components, and we consider a new edge, and we perform a join in case if it joins the two different connected components. If it is inside some connected component, we just discard it. So where's the place that allows us to have not a unique minimum spanning tree? Actually, this happens when we have several edges of the same weight, and these edges allow us to form to connect the same set of connected components differently. For example, if we have several edges of a current weight, let's say they're all of weight 7, then we may choose the different subset of these edges to add to a minimum spanning tree. For example, we may choose this, and this, or we may choose this, and this. But that happens not always when we have several edges of same weight. It may happen that there is still a unique way to form a minimum spanning tree. For example, if the edges are like this, there are edges that are already in connected components, we discard them. And if the edges that connect different components, if they form a forest, if they do not have any cycles, then we still are going to have a unique minimum spanning tree. So the criteria for us to fulfill is that for each value of an edge, all edges of this value, in respect to the connected components from smaller values of edges, they form a forest on these connected components. In the other words, they should not form a cycle. Okay, how to fulfill that? Let's move from the smaller edges to the larger edges. Consider some the overall idea of the algorithm. We consider the edges, the edge values one by one. We keep the connected components that are already joined together for sure. So at any moment of the algorithm, some edges are already added to the resulting minimum spanning tree. We are not going to change it. And we do the following things. Consider the edges of the current weight. For example, the weight is W. These edges are here. And there are already some connected components. So there are three possibilities that we may apply for each edge. For each edge, we may either reduce the cost, leave it the same, or increase the cost. For example, consider this edge. What happens when we reduce its cost? Actually, since these components are not connected using the edges of weight smaller than W, that means that if we reduce its weight to any number smaller than W, it will still be the part of minimum spanning tree, because at any moment these two connected components, they may be smaller at the previous moment. They are not connected, so we will always add it, and we can always add it pretty simply, because it will not form any cycles. So so all edges are divided into three categories. Those who are reduced, so we send them back to the past. those who are left the same, and those who are increased. What does it mean to reduce? Let me think. Reduce means that we send to the past and we join two connected components together. Okay, but leaving the same. Okay, after that we should leave the same some set of edges that do not form a cycle, and those who are sent to the future, meaning that we increase their weight, they first were sent to the future. Okay. We will not also consider. Will not only consider the edges of weight W. We will also consider those edges who have come from the past to us. So at the beginning of considering the edges of weight W, we have either edges that have the weight W or those who had the smaller weights, but we increase their weight up to W. Okay. So now we need to divide all edges into three categories. Into those who will be decreased, this is the first category, leaving the same or increased. These one are moved to the past. These one are processed now. And these one are sent to the future. Let's go like this. So once again, which edges can we send to the past? To the past, when we send in some edge to the past, for example, this edge is reduced, that means that we join these two components together. Note that we cannot simply send to the past any set of the edges we want. We cannot send to the past this, and this edge, for example, because they will form a cycle, and we do not want it. It is a useless operation. Well, we show that we will never send to the past several edges that form a cycle. So, when sending to the past, we actually join several connected components together. Okay, suppose that we have joined some connected components together. Now we have several connected components, and we should choose which edges are we going to process now, and which edges are we going to send to the future. Well, it's pretty easy. Well, actually, what we have left is the forest of edges, and we may calculate the number of edges that are going to be processed now. So the number of edges that are forming the spanning tree in some set of edges that we have currently. We can calculate their number simply by using the number of vertices, the number of edges, the number of connected components. It may be expressed using the number of edges in the spanning forest in the graph. It may be expressed using the number of vertices, edges, and connected components. So, what do we do now? Actually, here we do some kind of greedy algorithm. If we see some set of connected components that may be contracted together, we choose the set to contract such that the number of the edges that are going to be sent to the future is as small as possible, because sending them to the future, not only the number of edges that are going to be sent to the future, the number of edges that we need to send to the past, plus the number of edges that we need to send to the future, is as small as possible. Because this is exactly the number of edges that we need to change, and we want to minimize it. One may prove, I'm not going to prove it right now, that the following greedy algorithm is correct. Consider all sets that may be contracted. There are 2 raised to n of them. For each edge, calculate how many edges should be, for each set, calculate how many edges should be sent to the past and how many should be sent to the future. Find the best set among them and contract it. For example, if we contract this set, then we have to send, let us have this. We have to send, for example, this edge to the future and these two edges to the past. That means that we have to send 3 edges far away from here. So find the best set, contract it. After that, once again, find the best set, contract it, and perform such operations until you are done on this level, until contracting does not change anything. After that, proceed to the next way. Did anybody understand anything? It was a pretty hard problem. In the original contest, there was only one team who solved it properly. So it was a hard problem. And the idea here is to, once again, let me emphasize, the idea here is to consider edges starting from lower to higher ones and to carefully deal with the state of the graph at the current time, deciding which edge to send to the past and which are to be sent to the future. If you think more about that, I think you can restore what I just said. If there are any questions, I still can answer about it or about any other problems. Are there any questions? Does anybody have any questions regarding the editorial? Yes? In English, right? Okay, just like I did for the rest of the problems, right? Okay, I'll try to. Okay, I'll try to find. Okay, are there any other problems? If no, then let's make a short break.
Pode tentar, sabe se ainda tem folha essa folha? Vale. Eu queria que o resto do pessoal, acho que sim.
Thank you.
Pero bueno,
animar más.
Os argentinos estão te perguntando material, né?
você deu o microfone. Você deu o microfone pra ele ligado. Eu achei, eu falei, cara, será que é? Ó,
Hello, you're from the staff. This is my first day here.
First day. So we have to get your badge and your material.
Also, I haven't paid yet, so I can pay.
Yeah, you can pay after.
Rodolfo will send you some papers you have to pay.
You need to change dollars to real?
I have real.
Okay.
Okay, I'll give you the badge.
Só pergunta, sabe se ainda tem esse material na folha de hoje?
Or just send me an email. Let me. So what's the your name?
Não, você vai dar para você. Já voltei.
When you try
Pô, tá muito legal aqui, velho. Vou esperar começar a aula.
Eita, peraí. Cheguei isso não, tá Aí, tem 20 pés, mas tem 1000 aré.
Eu li ali no editorial que a ideia é exatamente
Igor, tem que dar tchau pra câmera. Tem que dar tchau pra câmera. Pô, mas ele não tá
Okay, let's continue back to the lecture. I think that today we are going to continue our talk about geometry because we have not really much time left. Let me just continue with several things I was not able to talk about yesterday. Okay, one more thing, although I've started to clean the problem D, I forgot to mention one important detail. Somebody asked me about how do we deal in this problem with precision issues. It was actually mentioned in the tutorial, I forgot to tell you, that using simply double here doesn't work well because double is not enough for doing the Gauss elimination on matrices of order larger than 20 or 30. If your matrix is at least 30 by 30, then one may give you the so-called ill-conditioned matrix. Those are the matrices that are very bad for algorithms like Gauss elimination. And you will never find the correct values of the coefficients. Like what you did was expressing V as a linear combination of B'ith, and alpha ith was equal to Kigi divided by Ki2 minus Ki1. So here you see alpha I is a fractional number, is a pretty arbitrary fractional number, and there are actually tests that do not allow for solutions using the fractional Gauss elimination to pass. So an important detail how to overcome that. Usually when the problem is integral and you need some kind of Gauss elimination, you may perform all operations not in real numbers but in some other field, and the most common field you may use here is you take all numbers modulo large prime number, like modulo 10 to 9 plus 7, and perform all operations modulo this number. What's the idea behind that? First of all, we have the vectors B'ith. Let's shorten them as possible. What does it mean? It means that B'ith are actually longer than X'ith. And it means that coefficients, when we consider linear combination of B'ith, may be fractional. Let's make them not fractional. What can we do in order to make them not fractional? Well, we have B'ith. Let's try to consider some integral vector that's proportional to B'ith but shorter. What is this vector? Well, actually, you should replace B'ith with B'ith divided by GCD of all its components, of Bi1, Bi2, and so on. If you divide it by GCD, it will still be integral because each component will remain integral, but it will be shorter, and X'ith will be no shorter than B'ith. It will be maybe B'ith multiplied by something, but not divided by something. That means that coefficients alpha I will become integral. They will be something integral. And what do we have next? Next, we were going to check if alpha I is positive or negative. When you replace the real numbers with residuals modulo some prime number, the notion of something being larger than something is usually has no sense, because how to compare which residual modulo 10 to 9 plus 7 is larger than another? They are all circular, so it's a nonsense. But in this problem, it is pretty well defined. Why? Because you see what you get here, alpha ith, they are all of some reasonable range. You know that if you could have used an absolutely precise doubles, you know that alpha I belong to the range from, I don't know which coordinates range was there, I think something like minus 10 to, let's say, minus 10 to 10 to 5th. You know that the real value of alpha I would be that. Also, you know that the alpha I is integral. That means that when you consider the alpha I modulo 10 to 9th plus 7, it will transform
to one of two ranges. The positive numbers will transform to 0 to 10 to 5th, and the negative numbers will transform to something like 10 to 9th plus 7 minus 10 to 5th, and 10 to 9 plus 7. So on the line that will look like the first few numbers, 10 to 5th, these are positive, and the numbers that are closer to 10 to 9 plus 7, these are negative. These are not positive or negative modular remainders, but these remainders correspond to the numbers that have small range and that were originally either negative or positive. So this is the way to understand if alpha ith was positive or negative originally. Okay, is there any question? Are there any questions? That's the useful idea how to avoid real numbers when dealing with Gauss elimination, because it works not really good with a large matrices. So if there are no more questions, I will proceed to geometry. Okay, let's discuss one useful algorithm that's still from two-dimensional geometry. One useful algorithm that is efficient and that often appears. This algorithm is location of the point inside the polygon, checking if the point is located inside the polygon in logarithmic time. Suppose that you have a polygon, a convex polygon. This is an important thing. It is possible to work with non-convex polygons still in logarithm of n, but the algorithms are pretty complex. I'm not going to tell you them. Okay, so we have a convex polygon and we have several queries. Each query is of form: is a given point inside the polygon or not? How are we going to check that? Well, let's first do the following. We know that if the polygon is convex, we know that we can triangulate this polygon. Let's represent it as a union of triangles that grow from the lower point of that polygon. This is the lowest point. As you remember, it is the point with the smallest y coordinate, then with the smallest x coordinate. So from all the lowest points, we choose the leftmost one. So the picture is like this. Then draw such triangles. What do we know about the points? All the points that we are asked about, first of all, they may be located either below this line or above this line. The points that are below the lowest point of the polygon, they are obviously not inside the polygon. So we may just compare when we compare the y coordinate to the y coordinate of a base point, this is a base point, if their y coordinate is smaller than the y coordinate of the lower point, we can just answer no, this point is not inside the polygon, and just not to do anything. Suppose that the y coordinate is exactly the same as for the lowest point. In this case, you should check if the query point belongs to the to the segment that belongs to this polygon on this line. It may be that there is a segment here, or in another case, it may be that polygon looks like this, so that on the lowest line there is only one point. Still, it is always a segment from x min to x max, and you should check if the point belongs here to this range. Okay, so the only thing that is left is the points that are strictly above this line. How do you deal with them? Well, let's continue these segments to race. So we have here, what do we have here? Here we have like several sectors in our upper half plane. Why do we need such sectors? Let's check that the point is inside the polygon in two steps. First of all, let's locate the sector this point is inside. For example, for this point, we'll try to find this sector. And after we found this sector, check that this point belongs to this triangle. If the point does not belong to the triangle lying in the sector that this point belongs to, then this point is obviously outside the polygon. So the basic idea, first, check the trivial cases. When y is smaller than y base or y is equal to y base, thank you very much. Then locate the sector point belongs to, and then check if point belongs to the triangle. How do we do the second step? For a given point, how do we find efficiently which sector contains this point? How do you think? We may use binary search, indeed. How can we use the binary search? Well, very easy in this case. A short few words about binary search. There are several ways how to write binary search, like using segments or half segments or intervals. Just do whatever you feel comfortable. Here, I think for me it would be easier to do the following. I put the L pointer over here, R pointer over here, and then just test each of the, try to choose the middle sum triangle. If it contains my point, then I have found it. If it is to the right of my point. But what does it mean that it is to the right from this point? It actually means that the left side of this triangle contains this point in its left half plane. It means that if the triangle, I usually enumerate the vertices in counterclockwise order. So this is 0 points, first point, second point, and so on. This is ith point, this is I plus 1th point. So it is to the right if the query point Q, this is the base point x0. So if Q minus x0 vector product with xi plus 1 minus x0 minus x0. If it is negative, then it is to the left. If Q minus x0 multiplied by xi minus x0, then, for example, here, then it is to the right of my triangle. Otherwise, we have found it. Okay, so the last thing is to check if point belongs to the triangle. By the way, how do we check if the point belongs to the triangle? How do you usually do that? How do you usually do that? Check testing if point belongs to the triangle. Somebody?
Yeah, that's the product of
Okay, one way is to consider three vector products. The point belongs to the triangle if it lies in this half plane, and this half plane. This is exactly what it means if the point belongs to the triangle or to the convex polygon in more general case. So three vector products like this by this by this, and this by this, for example, or another way, maybe somebody does it other way. The trigonometry. Sorry, once again. Using trigonometry, using some, or what? You told. Okay, never mind. So the other way that I prefer, that is maybe a bit simpler for you, is to check that the sum of this area plus this area plus this area, where areas are taken, the absolute values of areas, not the signed areas, is equal to the area of the whole triangle. This may be a bit simpler if you do not like to think what sign does the vector product has. Actually, if the point is inside, then S1 plus S2 plus S3 is always equal to the S of the triangle. And if it is outside anywhere, then the area will be larger by this excess, twice this excess. So the sum will be like, you see, this plus this plus this is larger than the area of the triangle. That's just a simple trick. Okay, so are there any questions regarding this algorithm? It works in all of log n per query, I think. Are there any questions? Yes. Sorry, can you speak louder? This part about the point? Okay. That was just a simple trick how to check if the point is inside the triangle. I claim that the point is inside the triangle if we calculate three triangle areas. The triangle, like, we calculate SXAB plus SXBC plus SXCA. If it is equal to SABC, then it is inside X. Otherwise, it is not. Otherwise, it will be larger than this. Areas may be calculated as a vector product, you know. Compared not areas, but twice the areas. That's the same, but does not require dividing the integer number by 2. Okay. Other, yes? Write bigger? No problem. I will try to write bigger. I think I won't rewrite this. Are there any questions regarding here? If there are any questions, can you repeat? Yes? Once again? For non-convex polygon? There are two kinds of algorithms for non-convex polygon. Both of them may be also implemented in logarithmic time, but they are much harder than this. One is like doing a scanning line, sweep line algorithm and keeping the division of our polygon in some persistent Cartesian tree, and the other one is another sweeping line, another complex data structure. Just never mind. I can send you a link to the article where they are described if you want. Yes?
What if the point is on the polygon?
Is on the polygon. You see, if the point is on the polygon over here, then we have checked it without any problems. And if the point is somewhere here or somewhere here, we still first try to find the sector that it contains. And after that, we just check that point is inside this triangle, meaning that inside also includes the border of triangle. This predicate also allows the point to be on the border of triangle. This will also be true if the point is... about the vector products. So let's you mean over here, right?
Because the vectorial products of these two vectors will be zero.
You are talking like this vector product, right? Okay. Consider this like the following. You have chosen some sector M. You have the point that you are testing. These two statements, they are related to the cases when the point is strictly to the left of it or strictly to the right. So these are two cases when you continue the binary search. If none of these holds, otherwise, we have found the sector, and it includes the case like this. In this case, this one will be greater than 0, and this one will be exactly 0. So both these conditions are not held, and you just go over here. Any other questions? Okay, let's continue. Let's go to the 3D geometry. Let's at least try to do that. Okay. So, 3D geometry problems are usually seem to be harder than 2D geometry, but in fact they are not usually hard from the algorithmic point of view. They are harder just to imagine and for you to know the basic primitives. If you know all the primitives for the 3D geometry, the 3D geometry problems they may be even easier than 2D geometry, because in 2D you should know some fast algorithms and so on. In 3D there are almost no fast algorithms. You just should be able to implement basic primitives. So, what are the basic primitives? Still, we have vectors. We identify points with vectors. So, what is the vector? Vector is 3 numbers x1, y1, and z1. Another vector is x2, y2, z2. There's some difference. Product of a vector and the number are defined as exactly as the same, and the scalar product is defined also as the same. That looks like I write smaller than needed, right? The interesting thing here is the vector product. For the plane, the vector product was a number, right? For the 3D space, the vector product is a vector, as one may think from its name. So how is it defined? First, let's start from the geometric point of view. What is the vector product? Suppose you have two vectors, v1 and v2, in the same plane. Well, they're always in the same plane, but still, here are these vectors. The vector product is always a vector that is orthogonal to both these two vectors. That also means that it is orthogonal to any of the vectors from this plane enclosing the v1 and v2. So this is a vector orthogonal to v1 and v2. It is looking in a specific direction. More precisely, V1, V2, and vector product should form a right, I forgot how to tell that in English, right hand, what? Right, how? Right hand rule, yes, of course it is a rule how to find out the direction of the last vector. I forgot the word, there was like right hand triplet or something like that. Right hand, okay. The direction of the vector product may be defined using the right hand rule. The V1 should look like your, how the fingers are called in English. Like your first finger, the V2 should look like your second finger, and the vector product like your third finger on the right hand. That's one way thing from the name. And the last thing, the length of V1 of vector product. Let me write using the should be equal to exactly the same thing as in the plane. In particular, when two vectors are collinear, they look in the same direction or in completely different directions. One is the opposite to another. The vector product will be 0. So that's what we want. Now, how this may be written in code? Actually, it is true that the vector product, the easiest way to remember its components is to write the following determinant. What does it mean? x1, x2, x3, and sorry, I've completely messed everything. Ex, ey, ez, x1, y1, z1, x2, y2, z2. This is mentioned in your paper. What does it mean? x1, y1, and z1, x2, y2, and z2 are the coordinates of the vectors, and ex, ey, and ez are the basis vectors. So our coordinate system, it is over here, is such that, okay, let's draw the more accurate thing. It should be oriented like this. The important thing, once again, the right-hand rule works only in case when your coordinate system is also right-hand. Actually, if you somehow mess with the coordinate lines, then all the signs may change. So try to always use the same coordinate system. It is easier. Usually people use like this coordinate system, or another way is to tell that this is x, this is y, and this is z. I prefer using that the horizontal plane is xy and the vertical line is z. So what are ex, ey, and ez? These are the basis vectors, ex, ey, and ez. Sometimes they are also called I, j, and k. What does that mean? It means that the vector product is ex multiplied by, so how is the determinant 3 by 3 computed? Ex, it is with coefficients y1, z2 minus y2, z1, plus ey with coefficients z2, x2 minus x1, z2, z1, x2 minus x1, z2, z2, x1, plus ez multiplied by x1, y2 minus x2, y1. So, but we know that Ex is 1, 0, 0, Ex, Ey is 0, 1, 0, Ez is 0, 0, 1. So we may rewrite it just by components. First component is y1 z2 minus y2 z1. Second component is z1 x2 minus z2 x1, and the third component is x1 y2 minus x2 y1. Let me check. y1 z2 minus z1 x2 minus x2 z2 x1 and x1 y2 minus x2. Yeah, yes, that's correct. So this is the formula for vector product in 3D space. It is not a simple number. It is a vector consisting of 3 components. Each of the components looks like the vector product in 2D plane. And the component for x contains only y's and z's. Component for y contains only x's and z's. And component for z contains only x's and y's. Do not mess with signs here. Try to, well, the good way to check that everything is correct, the letters over here should be like a circular shift of letters over here. For example, y transforms to z, z transforms to x, y transforms to z, z transforms to x. They transform by cycle like y to z to x. Something like that. Okay, this is the most important formula in the whole 3D geometry. Why is it so important? Because it allows us to do many cool things. Okay, this is not the only the most important formula. The other most important formula will be the mixed product. But before that, are there any questions about this? Questions? No questions. I think you may read that in paper 2, and it's pretty easy over there. So, 2 important formulas. This is the first important formula, and this is the second important formula. This is the coordinate representation, and this is the geometric fact. What is the geometric meaning of vector product? Well, this is the vector who is orthogonal to both of these, who is directed using the right-hand rule, and whose length is, by the way, what is this value? What is this geometric meaning? Yes, it's twice the area of this triangle, or the same thing, it's the area of parallelogram built by V1 and V2 in space. Note that V1 and V2, although I have drawn them like they are in XY plane, they may be, their direction may be arbitrary. The vector product will always be perpendicular to them and having the area length equal to the area of those two. In fact, if those two vectors are like expressed maybe in meters, they have some units, for example meters, then vector product is measured in squared meters. So these vectors are, if you scale or coordinates by 10, for example, then the vector product will scale by 100. So this is a second order vector. Okay, now let's talk about the mixed product. Mixed product of vectors V1, V2, let me write it. Okay, so what is the mixed product? Mixed product is a number that is defined like scalar product of V1 and vector product of V2 and V3. And if you look carefully on this formula, you'll see that it is also equal simply to a determinant that looks like this. Why? Well, because when you what you need to do is to take the product of x1 by this, and this is this minor of a matrix. So you take the sum of x1 multiplied by here we have v1 and v2, and here we have v2 and v3. So just imagine what happens when you draw when you take the scalar product of this with some new vector. Actually, coordinates of new vector replace these vectors, and you get the simple determinant like 3 of size 3. What's the geometric meaning of the mixed product? Well, it is also pretty simple. The geometric meaning is that it is an oriented volume of a parallelepiped built by V1, V2, and V3 as a side. Why so? Well, how to prove that easily? Well, because, for example, because you know there is a formula for an area of parallelepiped. Its area is the area of one of its faces multiplied by the height between the distance between two opposite faces of this kind. And actually over here, if you look on this representation, you'll see that what you are doing here is you take the scalar product of V1 and the vector that is perpendicular to this face and has the length equal to the area of this face. So their product is actually, it has length equal to the projection of V1 onto this vector, that is equal to the height of this parallelogram multiplied by the area of the face. So it is exactly the volume of parallelepiped. This allows us also to calculate the volume of tetrahedron. If we have a tetrahedron, I don't know how to pronounce it correctly, OABC, then the area of this tetrahedron may be calculated also using the mixed product. By the way, I claim that the area of this tetrahedron is actually a vector product, absolute value of vector product of mixed product OA, OB, OC divided by how many? I don't hear. By 6. Yes, correct. Actually, the volume of tetrahedron is 6 times smaller than the volume of the parallelepiped built by the same vectors. Okay. What's the geometric meaning of the sign of this mixed product? When is it positive? When is it negative? The idea here is following. Consider the, for example, the plane V2, V3. Consider it's the plane. You know that the vector product looks in some certain side from this plane. The vector product looks, in order to be to satisfy the right-hand rules of the vector products, will be looking somewhere over here on the picture of V2 and V3. So the sign of the mixed product will be positive if V1 faces the same side, and it will be negative if V1 faces the other side. In other words, the sign of mixed product is defined by the side which sum of the vectors looks in respect to the plane built by the other two vectors. Also, this mixed product is a skew symmetric value. That means that if you swap any of the coordinates, that means that you swap the rows in this determinant. And as you know, when you swap the rows in determinant, it changes its sign. Okay, another idea of how to understand the orientation of the sign of the mixed product is called the orientation of three vectors. Another idea how to understand the orientation of three vectors is following. Look at the picture from the end point of one of the vectors. For example, let's look from the end point of let's say of V1. We are looking over here. So here is the V1. It looks like straight on U. And here are V2 and V3. The orientation is positive if when looking at the end of V1 you see V2 and V3 making a counterclockwise turn, and it is negative otherwise. So if you have seen the picture, for example, like this, from V2 to V3 the shorter turn is clockwise, then the orientation would be negative. And it is zero, the mixed product is zero, its sign is zero, only if three vectors are coplanar. They belong to the same plane, and this is exactly can be derived from this from this determinant. You know that determinant is zero when the rows are when one of the rows can be expressed as a linear combination of another rows, when the rows are lying in a smaller dimension space, in a plane in our case. So this is the basics of vector products and mixed product, and we are almost out of time. Let's try to use it to what? Let's try to use it in order to, for example, intersect the line and a plane, or to find the shortest distance between two lines. Let's try to solve some problems. So, how do we define a plane in 3D space? Almost exactly the same as in a 2D space. We define the line. In the space, the plane is defined by a linear equation of form that is similar to a scalar product of A, B, and C, and X, Y, and Z equals to D. So ABC is similarly a scalar, a normal vector to the plane. It is orthogonal to this plane. Another way to define the plane is to present 3 points in the plane. The plane is defined by 3 points. So how do we transform from one representation to another? Suppose you have 3 points like P, Q, and R. How do you find the coefficients of the plane if you have P, Q, and R? Any ideas? Remember what we did in 2D case. In 2D case, we first found the normal vector, and then we found the free coefficient D. Here we should do exactly the same. How can we find the normal vector? Yes, we can just assume that A, B, C is a vector product of what? Of any two vectors that lie inside this plane. Which two non-collinear vectors we can choose inside this plane? Yes, for example, vectors PQ and PR. This vector product, cross product of PQ and PR, cross product and vector product is the same, is, according to the definition, a vector that is orthogonal to both PQ and PR, so it is orthogonal to the whole plane. So we may choose it as a normal vector. And after that we find this free coefficient D just by putting any of points P, Q or R into this equation and calculating the scalar product. Okay, that's good. Suppose that we have three points defining a plane. What was the name here? 3 points defining the plane CDE. And a line AB, and we want to find the intersection of the line AB with the plane CDE. How can we do that? Well as many other cases when we want to find the intersection of something with something, we may use the barycentric rule that we discussed yesterday. Let's try to find in which proportion x divides the segment AB. Actually, you may find that if you consider two tetrahedrons ADEC and tetrahedron, let me choose another marker, tetrahedron BCED, they share the same face. So the proportion between their areas is the same as proportion between the distances from A to this plane and from B to this plane. And it is proportional to AX to XB because there will be the similar right triangles, you see. So I claim that AX to XE, XB, sorry, is volume of let me double check. Volume of CDE ACDE to the volume of ACDE to CDEB. And what does it mean? That means that we can write an intersection point using a simple formula we already did several times. It is A multiplied by the volume of CDEB plus B multiplied by the volume of ACDE divided by the volume of the total volume, the sum of this volume and this volume. Actually, when you start writing a mixed products here, all these volumes can be expressed using the mixed products of several vectors. You will find out that this sum can also be represented as a mixed product of vector AB, CE and CD. That's just a trick similar to what happened when we found out the intersection of two segments of the plane. So this is, for example, how we can use the same barycentric rule when we calculate some intersections. Okay, let's talk about how we can use the vector products. This was an example how we can use the mixed products. Let's talk about the vector products a bit more, solve a simple problem, and then I think we'll finish our lecture today. So, the exercise. You have two lines. How can we define a line in 3D space? Well, actually defining a line in 3D space is always a bit messy, because in order to define it, you should provide one point on a line, and either 2 points on this line or 1 point and a direction vector. This is not really a convenient representation. For example, when you try to find the intersection line of two planes, there is no, at least I do not know an easy way to find the equation of the intersection line. What I usually do is that I have two planes, I intersect them with the third plane, I intersect them with another third plane, and 2 points of intersections are 2 points lying on the intersection line. So, okay, suppose you already have the two lines, one line and another line like A with the direction vector V, line like B with the direction vector U, and what you want is to find the distance between two lines. You may always find the distance between any two lines, actually, because for two lines there is always unique, almost always unique, the pair of points that gives us the shortest distance between these two lines. If the lines are parallel, then there is also a distance, but not unique pair of points gives us it. So how to find it? Well, a short fact. Suppose you have fixed one of the points on one of the lines. Then the distance from this point to this line, shortest distance is always attained on a segment that is perpendicular to the second line. Why that? Because if you look only on this point and this line, if you look only in plane that contains them, then the picture will be really simple, like this and this. And here it is clear that the shortest distance is on a perpendicular line. Any another will be longer because this is a hypotenuse and this is a cathode in this right triangle. So, okay, so we know that on an optimal XY segment, it is perpendicular both to line B, to this line and to this line, by the same reason. What does that mean? It means that XY is parallel to what? To which vector? It is perpendicular to this line and to this line. This line is defined by A and direction vector V, and this line is defined by B and direction vector U. I claim that XY is parallel to something here. To what? Vector product of whom? Sorry? U and V, correct. XY is parallel to the vector product of U and V. Okay. Consider this vector product, let's call it N. Let's not also only call it N, let's say that N, let's say that N is the vector product divided by its length. After we divide the vector by its length, its length becomes equal to 1. This is the way, I don't know if English has a proper name for that. In Russian it looks like there is a verb to norm a vector. I don't know, in English I never met it. So but when we divide the vector by its length, we make its length becomes 1, become a unit length vector. So now we have a unit length vector in direction that is parallel to the optimal answer. This is n. How can we use it? Well, we may use it pretty easy, I think. Actually, the xy segment is a projection. Actually, x is a projection of the whole line. Let's call this line L1 and this L2. Actually, x is the point of projection of the whole line L1 onto the vector n. Why? Because the line L1 is orthogonal to n, and when we start to project L1 onto any line parallel to n, when we project it, the whole line will be projected into the same point. So, get any so the length of xy is actually a projection of the vector BA, or xy is a projection of the vector AB onto the direction of n. Actually, once again, I claim that xy is the projection of vector AB onto the vector n. Why so? Because if we draw an optimal answer, it is parallel to n, and A projects to x and B projects to y. You know that the length of projection of vector AB onto the vector n is defined by the scalar product of AB and n. So I claim this is the answer to the problem. The scalar product of AB, A is an arbitrary point on L1 that is given to us, B is an arbitrary point on L2 that is given to us. This scalar product is exactly the distance between two lines. This is almost the great solution. It is almost complete, but if you write exactly this, you will get wrong answer on one small test. Which is that test? There is one case that we didn't consider here. Huh? At what zero? The lines are parallel, yes, exactly. When the lines are parallel, you cannot define the n vector like this. You should do something else. But when the lines are parallel, can we do anything simple here? I think when the lines are parallel, we have the scalar product AB multiplied by the vector product xy divided by the length of vector product xy. So AB projection minus, let me think. So when the lines are parallel, here we have A, here we have B, V and U are collinear. We need to somehow find the distance between these two lines. Actually, this is a two-dimensional problem, after all, because both two lines lie in the same plane. And the brute force solution would be to introduce the two-dimensional coordinates inside this plane. And after that, we are done. We may just use the two-dimensional solution. But it doesn't seem like a good solution. Let me think a bit about it. We need to find the distance between those two guys. We need to find the A. I can get this vector. This vector. Yeah, exactly. So we need to find this vector, the vector that connects two lines, and that is yes, the vector that connects two lines and that is orthogonal to both of them. We need still to find something like n. How can we do that? We know that n should be parallel, or it should be orthogonal to V. we may not write that n is orthogonal to u because it is fulfilled automatically. In this case, v is parallel to u. And n should belong to the plane that contains both v and BA, or AB, for example. That means that n should lie to the same plane with v and this vector. What does it mean? Well, let's find out the intermediate vector, vector p, that defines this plane. So let's get a vector product v multiplied by AB. This is a normal vector to the plane of our picture, so it how to draw it properly. So it's like it is perpendicular both to this and to this. Okay, and now we want to find n that is both perpendicular to v and to p. So n may be found as a vector product of p and v. And after that perform the similar things. So there are two cases in this problem, because when the lines are parallel we cannot simply take the vector product of v and u. And otherwise we cannot always use this way because it works only when n belongs to the same plane with v and AB. Okay, so sometimes you have to consider the vector products of some previous vector products and some composite long lines of vector products in order to find the directions or the planes that you are interested in. Is it clear what was the problem, how we solved it in the case when they are not parallel, and what was the issue and how we dealt with that? Are there any questions regarding this? Yes? How do you find the specific points x and y? Let me think about it. So how do you find the point x? The point x is the result of shifting a but by some vector that is proportional to v. Some vector, oh, that's easy. So what is the point x? You see on this picture we have three directions: the direction of v, direction of u, and direction of n. Consider the line L1 and the plane built by n and u. If you build the plane, this plane is exactly the plane that contains x, y, and b. So I can draw the vector n starting from here and get a plane that contains the line L2, and it also contains the answer xy, right? On the other side, x belongs to the line L1. So x is an intersection of line L1 and a plane that is passing through line B and containing u and n. So we know this plane, we know this line, and x is the intersection of that plane and that line. Similar to y. Any other questions? Okay. I think then we are finished. If there are any other questions regarding the editorial or the lecture, I can answer them.